about the floating points now. So for the floating point number, we have IEEE standard. This standard is actually major. Basically, all the laptop, mobile phone, and even your game console can support the IEEE floating point standard. So in the standard, they define the cases for rounding, overflow, underflow. But again, because this is a very comprehensive standard, so the hardware overhead to implement these standards is relatively high. Typically, the addition, subtraction, and multiplication are fast, but division is slow. So here is a binary number. Unlike the purest binaries, this binary actually has a response. So in this way, it can represent the value smaller than 1 by for example, this bit indicates minus 1, and this bit minus 2, and then 2 to minus 3. But you can use the same equation to calculate the decimal value of this number. Except k is not starting from a 0, but starting from a minus j. So these are some examples. Original fraction part and integer part. So the first example, the first one indicates the minus 2 to minus 1. Minus. So in this way, you can get the fraction. So the division can be done by a right shift. Multiplication can be done by a left shift. Right. number this should by 2, of course. And of course, you move this number left. Go back. Station by 2. IDs. You can but it always smaller than 1. So right. Very small. So the binary dot is not perfect because it can only help you represent some very small, very simple value. We'll use that. Binaries for reference. Why? Because bit width of these values. So some component for unlimited times. So this is the reason why we need those so-called floating point representations. The first component, the sign, the absolute sign. The 1 is a negative 1. That's the sign bit. The second part is this. M is a value from 1 or larger. And the E is the maximum. So it contains 3 components. And it can be represented like this. It's not the exponent itself, but it includes. Also, the fraction encodes the capitalized M. It's not the M itself. So this is the format. So in order to implement this format, you have different options. It has 32 bits total. So 1 bit for X. Fraction. You can also vary double variable has a 64 bits. Besides these, some other machine also support larger bits. It's not common, but some CPU do. So let's talk about the most common case where the EXP is not all zero, not all, and not all one. Then the sign bit is single. If it's a negative, then it's a 1. Then if it's a positive, it's a 0. This is the same as the find binaries or two's complement value. But the encoding of can be represented by this equation. So the EXP minus 5 exponent. So different floating point, single procession floating point, double procession. And this 5 can be represented by number of exponent bits. So let's go back to the previous slide. You can see for the single procession, the EXP has 8 bits. For this 8 bits, two to eight can represent 0. Because we are talking about the EXP, which is not all 0 or all 1. So this one from 1 to 2. So this is why we select the file because we want to represent the rank, multiply this rank. This bias can help you to modify this rank. Move this rank, move the 0 to the center of this rank. So if you have 11 bits for the EX, the 11 bits can represent from 0 to 2. This value is because it cannot be all zeros, and it cannot be all ones. We will discuss the cases for all 0 and all ones, but in this common case, it's not, the ESP cannot be 0 or all ones. So this is the rank. If this is rank, then the bias is this value. So this value can help you to modify this rank, move the 0 to the center of this rank. So after you minus the bias, this is new rank. The function of subtracting a bias is that move the 0 to the center or to the middle of this rank. This is how the encoding for the EXP happens. For the app, always write the app. So the m is always starting from a 1. And then the fraction will be the least after fraction. So this is the minimum value. So if the m is always starting from 1, then you don't need to store that one. So the storage of that one is actually free. So here is one example. So how to represent by the IEEE floating point standard. Single procession, of course. Let's try an easy one, single procession. The first step is to write that decimal floating point number to its binary form. So this is the and we can rewrite this number like this. So why do we want to do this? Because we want to calculate the m, capitalize the m, and capitalize the e. And you can see that after we do this, and the easily write so after we get the m, we can calculate the fraction. So let's revisit the standard. For the single procession standard, the fraction has 23 bits. But you can see that from here, and adding the 0 to 23 bits. then this is the 23 fraction. And please notice that we don't have, in the standard, every number has the mean, so we just ignore it. So the first one is, and then we calculate the EXP. So we know the actual number 13 and 5. So we just add there. So we have 8 bits. Okay. Again, in the standard, we have 8 bits. Yeah. So the EXP is oh, good. So I have a question. So we have 13 and fraction is 23 bits. Why do we don't have all zeros here, but not this? We don't have some 0, 0, 0, 1, 1, 2. But we have. Why? So if we have this single digit one, if I ask you to represent this value by 4 bits, you will write something, some number like this. So you actually had 0 before this. But here we add 1. We add 0 after. Why do we want this? This is because you can see that these values are actually smaller than 1. So they are fractions. For the fraction, we add. If we add a 0 before, we actually divide this number by a lot of 2. So that's not the value we want to represent. But if we add here, this number is 0. Now, but here, if this EXP is 1, then you have 7 zeros. This is different. Because this EXP is actually some value larger than that. So we add 0 before that. This is this value for the EXP and this value for the M, capitalize the M. The first one is the for and then we can use right put these numbers IEEE floating point single projection format. The first is actually the fine because it's a positive number, so it's a 0. Then we put the EXP to the next level. And then for the other rest, for the capitalized app. Any question? So we have a 1, 3, 5, and 8 bits for the capitalized app and 23 bits for the capitalized. I'm sorry, 8 bits for the capitalized E and 23 bits for the capitalized app. And then we can talk about what if EXP is all zeros. When the EXP is all zeros, we actually represent a value which close to 0. And then the leading bit for that. So in this way, you can see this is a value smaller than 1. So if the EXP and function are all 0, then it can be used to represent 0. If the EXP is all zeros, the fraction is not 0, then this is smaller than 1 value. It is close to 0. Smaller than 1 or larger than -1. So it will lose precision when they decrease. So which means that if you use this format to represent a very small value close to 0, maybe this format will approximate that number at 0. So in this way, you will have some kind of. The underflow problem is you want to represent a very small number, but this format accidentally use a real zero to represent that small number. Then in this case, you actually lose that number. So another special case is the EXP is all ones. So when the EXP is all ones, all zeros is infinity. And of course, you can have a positive infinity and negative infinity. If the fraction is not zeros, then it's not a number. That's not a valid number. So by different values of EXP, we can prove the format, the IEEE standard format, into different cases. The most common case is EXP is not all zeros, all ones. So if EXP is all zeros, it can represent 0, all a very small value, each close to 0. larger than -1, but smaller than 1. And the last case is the activity is all 1. So if the fraction is all zeros, then it's an infinity, positive infinity and negative infinity. If the fraction is not all zeros, then it's not a number. So in some low-end computers, you can even have 8-bit floating point representations. 1 bit for the 5, 3 for the 10. 4 bits for the 10. Again, if you have 3 bits for the 4 bits. 4 bits can represent from 0 to 15. Now we only discuss the common cases from 1. It cannot be all 1. So the rank now be modified from 1 to 14. And then the bias is 7, so it can help you modify this rank and move the center of this rank from -6 to 7. So you can see that no matter you use 8 bits, 32 bits, or 64 bits to represent the IEEE floating point number, we follow the same principle. So this table summarizes capitalize and capitalize E. Again, we use the value of the if it's all zero, then we should say that we should see the fraction. If the fraction is a 0, then it represents a 0. If the fraction is not a 0, then or not a number. So all the other states you can use the method in pure slice to compute the value. So even you have an IEEE standard, you still need to do some rounding. Because you have a limited number of bits to represent the capitalized E and capitalize the M. If your value larger than, need more bits, so you have to, do some rounding and give up some bits. There are 4 different methods to do the rounding. So the last assume that you can only see the value, 3 digits value. Then the 4 digits first method less than half. Less than half when we apply plus one by this 4 all the digits. But if it's a 2, 3, 5, then this is because this is 5, larger. In the complete run out. If it's a long time, if you run out, so this the rundown for the cases when the exp is 0 are all zeros. Why? Because this case can close to 0. And then your round down scheme have a very important impact. Here is a summary. Normal value for 8-bit standard. So here is some characteristics attribute standard. So the floating point 0 is the same as the integer value, integer 0, because all bits are all zeros. So the first bit always and we also need to negative 0 and positive. So the IEEE standard actually have 2 zeros, negative 0 and positive. So if a number is not enough, it's better if you compare a not number with a number, then the not number is always larger than other values. Because if you have a arithmetic operation or a logic operation involve a not number, the result should always, which means that you need to avoid this case. And then the IEEE standard helps you handle denormalized case, which means you use that format to represent a very small number. And if you represent value by the IEEE standard floating point format, then you actually somehow do the approximation because you need to feed that value into a fixed bit value. Then you have to do some rounding modes. So this table summarizes and we do the rounding mode on the binary bits. So we call a number even when the least significant bit is 0. And the halfway means when the bits to the right of rounding position. So here is all values. After the binary plot. So if our target to be found, and 30 here is 1. Because all of them, we have carry. This is the raw out, this is the raw out. Even in the binary, for the binary bits, you have a different round modes. So the arithmetic operation can happen directly on the IEEE numbers. So in order to multiply to floating point level, you need to yes. So compute XOR between the sum bits of two values. And do a multiplication binary 2m's and addition between two e's. Even after you sum the multiplication. Do some fixing operation. Because the arm is between 0 I'm sorry, one larger on larger than 2, then you need to increase. Larger than 2 means you have to value. Then you need to move the primary point to here. How to do that? Just plot on one. And then you need to check whether the E is in these ranges. Whether the E can be represented by 8 bits or some other fixed number of bits. If it cannot represent that, it's an overflow. And the result must need more than you need to use your round model, round mode. 23 again. In all the operations here, the most multiplication. But again, the floating point is more expensive than integer one because all compared to the multiplication, the addition is simpler. But after the addition, by addition, I also include subtractions here. After the real arithmetic operation, you also need to do the fixing operation. The fixing operation can help you to convert the result to the IEEE standard again, and make sure there's no overflow. So all the properties of integer can be applied on the floating point numbers, except the associativity. The associativity means for the integer addition, you have something like this. But you cannot do this for floating point numbers because you may suffer from the overflow problem. So in the floating point number, we don't have this. Again, in the floating point multiplication, we do not have this law either. Because of the overflow or rounding problem. Besides this one, we may not be able to do this for the floating point method. Also because the overflow. So in the C language, we have two different floating points. So directly convert these values to integer or long are actually very dangerous. Because in some extreme cases, you will lose that value or have overflow. So for your Hello World application, it is not matter, but for some application require very high precision, like satellites, it can help you. It can introduce significant damage. Any question? So I think the most important part is that you can understand this format. The most important part that format. And then you can understand this example. How to convert the number to this binary attribute standard binaries, step by step. Why we do this first and why we do that second. So if you can understand this example, I don't think you have any problem. Just understand the most common case first. Any question? If no question, we can stop today. Thank you very much.